Let's prove something, right? We're going to prove together that 2 plus 2 equals 4. Now, Russell and Whitehead, back in like the early 1900s, right? They had like several volumes on, Principia Mathematica to like to create logic in some ways. There was logic beforehand, but it had some issues. So they wanted to create logic, and they spent like, 400 pages to eventually get to the point where they can prove that 2 plus 2 is equal to 4, and it's a really long, complicated proof because they're very detailed, right? Okay, now let's do it together with modern type theory. The proof object is flat, right? And we're done. Right? How is that even a proof? We didn't even do anything. All right. Well, we'll check it here, right? So we know that splat has type top, our logical truth value. So now the question becomes, can we use that conversion rule to convert 2 plus 2 equal to 4 into top? All right. Well, let's try it. So let's do some reductions here. 2 plus 2 is equal to 4. Now this plus thing evaluates under our computation rule for plus, and if you do some massaging of the recursion stuff, you'll find that that is in fact 4. Now we have this natural number function, equality of the natural number functions that returns a Boolean, whether the inputs of the same natural number or not. And you crank the handle on that and you do the recursion and you do the reductions, and you'll find that it basically strips off a successor of successor of successor until it reduces down to 0 is equal to 0. And then it hits its base case and it says, yes, 0 is equal to 0. And that reduces to the Boolean truth value. Now we run the angle brackets over here, and that's just an if statement that says if t, then top else bottom, but t is in fact t, so that runs the if case, and we get logical tautology top. And you're like, yes, this type here matches, right? So these two types are convertible, and so this flat here is in fact a valid proof of that expression over there.
So is this like part of the magic of dependent types, where we can kind of lift up these Boolean expressions into sort of logical truth or falsity?
Yes. So the point is that because we've unified the language of programming and logic, right? We can use programming we can use the programming aspect of our language to simplify our proofs by doing computation inside the proof itself. And so this is called the Poincare principle. It said something like "let us compute," right? So so it's just that when you have a problem that is computationally oriented, right? There's nothing to prove. You can just run the computation. You can just run. Let's do something a little bit more interesting. Where we can't just use this reflection principle. We want to prove that for every natural number, n is equal to n plus 0. Right, and this is the proof over here. Sorry, that C of n is an error. In fact, I didn't finish off this proof. No, it's fine. It's just. Let me fix that. Can I fix that easily? I want to fix it.
Live coding.
Yeah.
Hotfix.
Oh. Now I have to go through all this. That's a huge mistake. Okay, right, that's the proof. If you'll indulge a bit of syntax and hand wavings, right, I'm just going to rewrite the proof this way, which is a little bit easier to see. This is a little bit more Haskell-y, right? It can almost systematically be converted to the previous expression that we had over there. And we're just going to say that there are two cases that we have to consider, the 0 case and successor case. The 0 case returns flat, and the successor case just recursively calls itself on the smaller value, right? This is the proof, and it's kind of obscene, again, from a computational perspective, because this function, right, it just runs itself until it gets down to 0 and returns flat. But that's the proof of this, and we'll go over it, right? So there are two branches to check, the 0 branch and the successor branch. And to check the 0 branch, right, we need to make sure, so what is the type of the 0 branch? What we do is we end up basically taking this for all expression that we had over here, and we substitute 0 in for all the occurrences of n for this branch over here. This is the heart of dependent case analysis, right? The types of these two branches are actually different. The type of this branch is this expression with n replaced by 0, and the type of this branch is this expression with n replaced by s of m in all locations, right? This is the heart of what makes dependent type theory different from regular type theory. So when you do case analysis, your branches can have different types. I remember Conor McBride told me, he was talking about the problems with simple type theory, and simple type systems, like every type system you program with, that if you have an if statement, right, you can swap the two branches in any if statement in your program, right, and it will still type check because the typing context can't distinguish between those two branches, right? So, right, this entire class of like errors of swapping, like it's not maybe necessarily the type of error you would make, right? But like type systems cannot capture that level of logic, well, correctness, right? It cannot capture you've not swapped the branches in your if statement, right? Dependent type theory can, because you have the potential, you have the ability for those two branches of what would be your two case statements to have different types.
Like you mentioned, you said that this is not an error that we would actually make. I think they said 3 or 4 times today, actually.
Oh, okay. So
yeah.
It depends a lot on your programming context, I guess. Yeah. So in this branch, we have to show that lemma 0 has this type. Here, I've replaced all the m's with zeros, and then we can start evaluating, right? Plus 0, that is 0. 0 equal to 0, that's true. True, the lifting of the Boolean true to the logical level is top, right? And we check our body of our Latin expression, it has type top, so we have type check, we're good. Let's do the other branch. We have to have that level 1 of s of m. We substitute s of n for all these things over here. This sort of goes into the details of how plus and equality is implemented, and in fact, it's very important for the correctness of the proof to understand how it's implemented, but this is typically how you would implement them. Again, successor of m plus 0, what that does is it strips off the successor, recursively calls plus, and adds the successor on the back. So it adds sort of this set of parentheses over here as its step. So here, we're taking advantage of partial reduction, which is a very important aspect of dependent type theory, that even though we're in a context where we haven't like filled in exactly what this variable m is, we can still perform reductions, even in the presence of unknown variables. And we can try to reduce as far as we can, and maybe we'll get stuck. At this point, we can't reduce plus anymore because it has to be recursion on m, and m is a free variable, there's nothing we can do about it. So I get stuck at this point here, but this is actually far enough to let equality start proceeding, because the way equality works is it basically strips off successor symbols and checks to see if you get 2 zeros at the end. So equality will strip off 2 successor symbols and recursively call itself on this sub-expression over here. And lo and behold, the body of our case here is lemma m has that type over here, right? So even though we weren't able to completely reduce this expression, we reduced it far enough to get this to type check, and so we are good. And so that type checks. And that is our proof. Here's another proof. I won't go into as much detail. We want to show that for all n and m, that if n is equal to m, then m is equal to n, right? So this is the symmetry property of equality, and this is what the proof looks like, again, over here. Here we have, sorry, there should be an h over here. Looking at this one time. But this hypothesis, which is the logical hypothesis, just becomes a variable name. Another variable for our function, and we can do things with it, like pass it recursively to itself. And in fact, in these cases over here, what happens is that in these cases, this reduces to false, and this also reduces to logical falsity. And though false itself is not provable, false implies false is provable, because you just take your false that you have and you hand it off as your answer, right? And that's exactly what it does over here. So we have this hypothetical proof of false, right? We'll never get into this case, right? But you want me to prove false, and I'll just take my hypothetical proof of false and hand it off to you, and then you can have your hypothetical proof of false. Right, so, let's see here. What's my next slide? Right. So this is all toys, right? But this really works. Like this really works, right? So